This is an example of a method of cuts for finding these internal forces. This problem states that there's a member ABC and brace BD, and they are used to suspend an electrical transmission line from a utility pole. And we're supposed to determine the internal forces acting on cross-sections E and F, which are located immediately to the left of point A and to the right of point B, respectively. These terms immediately to the left and right of these points are a very important concept to kind of think about when we look at this pole and what we're trying to analyze. We're trying to analyze this cut here and this cut here. And essentially when they're saying immediately, we know there's this force that's acting on it right at this location, but it's immediately to it, so it's like right up to it, but not at it. So it's very infinitesimally small when we draw this. So essentially a moment arm at this location would be essentially 0 for us. So let's take a look at this problem. Let's take a look at cut E first, and then we'll take a cut at F. So let me draw the free body diagram for E. Okay, so here's the free body diagram. One thing I wanted to point out to you is how I created this diagram and what I decided to do. So if we look at this original diagram up above, we see we have this angled bar coming down, and I wanted to align my coordinate systems with that because most of my forces are in that direction. So if I look at that, my NE is in like the X direction, my V sub E, which is along the shear along the cut, is in my Y direction. So the only force that I have that is not in this new coordinate system, non-horizontal vertical type coordinate system, is this 400-pound one. So I just need the angle between that, and I can work this problem out. All right. So the first step is to start solving for these forces. I can sum forces in the X direction. If I do that, we have some of the forces in the X equals 0. I have a minus NE. I have a plus 400 pounds times the sine of 30 degrees, and that's all I have because that is this component here is the sine of that. That gives me NE is equal to 200 pounds. And notice that it came out positive, and in this case that really does mean tension for us. Next, I'm going to sum forces in the Y direction. And if I do that, I have V sub E, my shear, at E minus 400 cosine 30 degrees. That gives V sub E is equal to 346.4 pounds. Last is I need to solve for my moments. And I'm going to take my moments at that cut. So I'm going to take the moments at M sub E, this cut area where I cut it. Now if you remember in the problem, it said that it is immediately to the left, right, of this point. So if I look at that, if this distance is immediately to it, essentially it's infinitesimally small, or we will say it is 0. Okay? So if I do that, then I have my moment is equal to a minus M sub E, the moment, the internal moment, and that is all I have. So M sub E equals 0. Okay? So that's what it means when it's immediately to the left of point E. Now if we look at this other one, which I'm going to do next, is I'm going to look at it being immediately to the right of point B. So if I'm looking immediately to the right of point B, it means that I'm not going to include the force in this 2-force member. Notice that that is a 2-force member. because it is just to the right, so I don't include that in my free body diagram. So let me draw that free body diagram. Okay, so I've drawn the free body diagram for this section at F, our cut at point F. I've drawn in our internal forces for that section. We see the only difference between this one and the other one, as far as the free body diagram, is that we have this length of 24 inches from our original free body diagram that we analyzed. Again, we're taking it immediately to the right, so we do not include this force. That force is not included in our free body diagram. So let's take a look at solving for our shear and normal force. And we see if we look at our shear and normal force, they are exactly the same as our previous free body diagram, so nothing really has changed in here, right? We haven't added any additional forces in the x or y direction, so we have the same results. Let me write those equations now. Okay, so if you look at this, these are the exact same equations that I had before from the previous one, because there is no, like I said, additional forces on our free body diagram. So the next part is to draw our, or not draw, but to write our moment equation. So if I start writing our moment equation, I'm going to have the sum of the moments, and I'm going to take it at F, which again is immediately to the right of that point, B. I'm going to have that equal to 0. I will have a minus m sub f, which is the moment at that cut, my internal moment, minus I have the component of this 400-pound force, which will cause a moment in the clockwise directions, which will be a minus. The other component, of course, is in line with it, so that will not cause a moment. So let's write what that is. Again, that will be minus 400 pounds cosine 30 degrees. That's the component that we've shown here. And then we have our distance that we're going, our moment arm, and that is the 24 inches that we're going. Solving for this, we get m sub f equals minus 8,314 inch-pounds. Okay, so that was very interesting. We solved the problem for these two locations, here and here. The one thing we didn't do is we didn't say, oh, what happens if we cut it on the other side of B, right? Just immediately to the left of B. So let's take a look at cut G and see how cut G varies from cut F. Okay, so I'm going to draw that free body diagram over on this side. We'll keep it on the same page then and take a look at how these two compare. But I will draw the free body diagram. Okay, so I drew the free body diagram, and we see that we are now immediately to the left of point B. We've now introduced this force at B. And if we count our unknowns, though, we have 1, 2, 3, 4 unknowns. So now we can't really solve this free body diagram. What do we do? And I bring this example up because I know that it happens in your homework a lot of times, and things might happen like this. So what do I do? Well, what I can do is I can draw one more free body diagram and draw it for this whole system, right? And then solve for either this unknown here, or I could solve for my reaction forces at C. So let's draw that free body diagram. Okay, so here's my free body diagram for this. I do still need to put in my coordinate system for it. So let's just draw that in. I'm going to pick the same one that I've been using. You'll see a few things. I've put in my pin reaction forces for this, and I've made them aligned with my XY system. I can do that. I still have my B, which is a two-force member, which is acting on it, and then I have this 400-pound force. If I would have made B into an X and Y component, I wouldn't have, I'd have too many unknowns at that point, but because I know the angle, I've reduced one of those unknowns. So now I know B, and I have B as an unknown, CY and CX as an unknown. Okay, we use the same methods typically for solving this type of problem. For unknowns, we take a moment at one of the points, then we sum our forces in the X and Y. I'm going to do this one a little differently. Typically, I sum my moments at like point C to get rid of those two unknowns, but I'm just going to do this one differently and solve it at B. I'm going to sum moments at B and say that that equals 0. If I do that, I will have my minus 400 pounds times the cosine of 30 times the 24 inches. I have plus CY, CY times the 24 inches, right? That's just CY times the 24, and that should equal 0, and I can get CY then, which will equal 346.4 pounds. So now if I sum forces, in the y direction, if I do that, I will have, of course, my minus CY, which is a minus 346.4 pounds, minus 400 cosine 30, and plus B cosine 30. We can solve for B, and B will equal 800 pounds. Last, we just need to sum forces in the X direction. So summing forces in the X direction, I don't think I can get it all in there, that's all right though. Sum forces in the X equals 0. I have a minus CX plus my 800 pounds times the sine of 30 degrees plus 400 times the sine of 30 degrees. And then I get CX is equal to 600 pounds. Okay, so really I could have stopped with just B because I needed to know B at this location. But now that I know B, we said B is equal to, what did we say, 800 pounds. I can now solve for my forces at this location. So first I'm going to take a look and solve for the shear force. I'm going to sum forces in the y direction. So I'm going to sum forces in the y direction equals 0. If I do that, I will have 800 times the sine, that should be cosine 30 degrees minus 400 cosine 30 degrees, and then minus VG. And we will see VG is equal to 600, minus 346.4 pounds. So then I'm going to sum forces in the X direction. And if I do that, I have a minus NG. I have plus 800 sine 30 degrees plus 400 sine 30 degrees. NG will equal 600 pounds. And last, we will do our moment. We'll sum our moments at this cut at B, essentially. And remember, it's infinitesimally close to B. If I do that, I have a minus mg, and then I have a minus 400 times the cosine of 30 degrees, and my distance is 24 inches. mg, my moment at G, then equals a minus 8,314 inch-pounds. Notice I didn't bring in B itself, this vector B, because V again is infinitesimally small. It's right at that location. So real quickly, we could have want to kind of compare between the two. We see we have a large jump in our axial load due to that force being added in. Our shear essentially has shifted in directions, which is kind of interesting. And then our moment, though, is really the same at that location. So the moment hasn't changed, but we have a real big jump in our axial load. I could have done this also by, instead of taking this, continuing to cut from this side of this diagram, I could have cut instead from the other side. I'll draw a free body diagram of that, show you the solution. I'm not going to run through that, but I will post it right on here for you so you can see that. Okay, so I've done the solution using the other side of our free body diagram. So I made our cut essentially at G again here. I'm looking at the this other side, this left side. I have not included, of course, this force here, this B force, because I'm immediately to the right and I'm looking to the right. So you will see that it does not exist in my free body diagram here. It's just to this other side. It's over here kind of pulling in, so we don't have that included. You'll also note that I was very deliberate in making sure that my direction of these forces are opposite the direction of the cut from the previous side, so everything balances out and everything is in equilibrium internally to this system. I then summed forces in the x direction, which is a very simple one for this case, and then some forces in the y, and then did our moment at that location. And you'll see that I got the exact same answer. So either method is fine when doing that, taking either free body diagram. We should get the same results, and we do. If you have questions on this, please let me know.